So today we'll start with sequence and series. Then for the next section, I will start talking about optimization and various numerical techniques. So today I would like to cover various important concepts such as sequence, convergence sequence, divergence sequence, various criteria to test whether the sequence is convergent or not, whether we have convergence, what do we mean by rate of convergence, radius of convergence. So we'll try to see as many concepts as possible today. If we left to talk about some topics, then we can discuss in further classes. So first I would like to tell you that what do we mean by a sequence. So as professor said in the class, definition for the sequence is basically we have a number. So it's what? Okay, let's start then. So we have a definition of sequence here. Basically, it's a function not allows me to write. So basically, we have a function in which the idea is that the input is integers, especially the positive natural numbers, in which we map using this natural numbers to the other right hand side, where you can see over here. Just a minute. Actually, my pencil is not charged here. To wait for a while. By the time I'll just go through the PDF of this. I will upload this PDF in the Google Drive. You can check them. Basically, this PDF talks all about the definitions, various exercises, examples. Consider like what this kind of typical function look like as a language of as a language of function. As you can see, in case of example one, we have a sequence called as fn equal to fn square, and we can see the mapping here. We see it's 1-1 mapping in this case. In second example, we can again say it's 1-to-1 mapping, but in third example, we can say it's many to one mapping. So all these are the valid mapping. Okay. So in the third example, we can see in which all the elements of the sequence is one. So that's a convergence sequence because we have convergence. If we apply the definition of convergence here, it will be a valid definition. And the idea in the second case, the second example, we can see it's a very trivial 1 over n cube, in which if we take the n equal to infinity, n tends to infinity, we see the elements converges to 0. So the next question immediately comes that what if we add all the elements of this 1 over n cube, whether this would be convergent or divergent, that would be an important question to answer. Okay, so in the case of fourth example, we can see that's an oscillatory function, right? It's an oscillatory mapping here. So the oscillatory mapping is an example in which if you consider subsequences, those 6 subsequences can be convergent, but there always exists at least one subsequent for which it is not convergent. That's why this sequence is not convergent. The idea is that if we have a convergent sequence, no matter what subsequence you create out of it, that should also be convergent, right? So if I found any subsequence which is not convergent, then we claim that the original sequence is not convergent. So that's an important idea which I can tell you from this particular example. I'm not going to repeat all the definitions because all the things are there already in the video. I'll talk I'll talk mostly on the ideas and how to apply them. Okay. So as you have seen, what do you mean by finite sequences, infinite sequences? Finite sequences in which the number of elements is finite, and infinite sequences in which the number of elements of a sequence is infinite. And finite sequences can be seen as basically where the if we consider the input set, that is definitely an integer, but that is closed integer. For example, it starts from 1 and it closes from 100. That's what it is. For an infinite sequence, we might more be interested in which the limiting value of the sequence. So we would be interested in, for example, like what if n tends to infinity, whether the sequence is convergent or not. Where do we see some behavior, for example, increasing or decreasing? Uh, do we see some monotonic behavior? Monotonic in the sense that it is strictly increasing or strictly decreasing. We are also interested in the idea that is bounded or not, because the moment we see that a sequence is bounded and a monotonic, increasing, decreasing, then we can immediately say the sequence is convergent. That's why we are also interested in the, such as the bounds on the sequence. Okay. Then we also define something called as bounded subsequence, because if we know the sequence is bounded, we also know that we can always construct subsequences first such that they are also bounded. So, for example, it is sometimes very hard to prove whether the sequence is bounded or not. So, what do? We consider various possibilities of sequences, subsequence, then check the convergence of that, the boundedness of the subsequence. So, I'll basically I'll write everything. For now, I'm just giving you the digression what I'm interested today talk. So, basically, you can always have a map in which the map looks like this way. For example, this is your n and this is your fn function. So what do we see here? We see that there is a function f which maps natural numbers to the real numbers. Okay? And this function takes integers and maps you to some real number. For example, in this case, let's say n square. So what do you see here? So you will see basically a function, but not a continuous function. It will be a discrete function, but those points which you see in the graph turns out to be subset of the original continuous function. For example, this looks like a continuous function, and it is, but the difference is that the input is an integer. So what kind of things you will see here? Like, for example, these are my let's say 1 2. So for 1 will be 1 square, 1 will be 1 just 1. For 2 it will be 4. So you can see here turns out to be this. So this fx is actually x squared, but over here you can see some points here. So this purple dots actually belongs to this fn, okay, but not the whole red dot. Red line basically represents some continuous function. Okay, so when you try to join, when you try to fit a curve to these points, which is generated because of this 1 comma fn f1 1 comma f2, and if you try to join them, you try to fit a curve, you'll see that that fit curve is actually an x square. So you can see that sequence is basically a a special selection of a point from a sequence. I'm sorry, from a function. For example, over here the function is this. So in order to create a sequence, what do? Check the outputs at the integer inputs, at the natural inputs. So basically this is what your sequence is like for over here. So this is what we see here. So this is what it looks. And here is one of the example in which you can see a discrete points. For example, over here you can see here. So you can see it's some kind of an oscillatory behavior. So if I try to basically fit a curve to this point, it seems like this seems to follow this kind of a path. I can fit this curve, right? So this seems to be some oscillatory which gets converged to 0, right? Seems like. So you can see that there is some function, there exists some function, an oscillatory function. To me, this looks like some kind of 2, minus 2 sine x, I guess. This is what this will fix this. and you can see okay, there is some damping factor as well. Let me add this damping factor minus x sin x, yeah. And you can see what I'm doing here. Basically, I'm selecting special points from this function, this, this, this. Okay, so this might not be this. It might be equal to some, yeah, might be this. I don't know. So you can check. You can check them. So that's what we are doing here. Instead of looking the continuous behavior, we are only looking at the discrete inputs, and that discrete input is basically a natural number. So we are just looking into this mapping, n to r mapping over here. So okay, so let me begin the idea here. As you can see in this sequence, the mapping is done from 1 to n, which are the integer set, to the r set. But you can see how they are mapped. They are mapped as some sort of square function, right? Some sort of square function. It's mapped like this. So we always represent the sequences as this, where it starts from some n, and let's say it ends like maybe for 10, for example, and we call them as to be some finite sequence. This is all about definition and all. Now let's get to the main point. So the main point is that the limit of a sequence. So if some sequence is given to me over here, for example, so this is nothing but the same thing, okay? The way we represent sequence. So there are it depends on what author wants to represent the way. So this is basically this, nothing new, okay? And the statement tells you that the sequence turns out to be convergent. I can say there exists a limit L such that when you take a large integer, very large integer, and you want to see what is the mapping of that very large integer, it turns out to be some L. So this is again the idea of limits, right? Again, same idea of limits, good old limits definition, I would say. The only difference is that instead of talking in the terms of continuous, now you are talking in the terms of steps. Okay, so what you're basically doing here is basically, let's say you have this limiting value L, and you start from here, this A1, A2, A3, A4, A5. You can see you're taking a jumps, right? Discrete jumps. But let's say we have taken infinite number of jumps, and we are labeling those jumps with the integer n. Okay, so A1 basically tells you the first jump, right? So starting point, you can say. So starting point, then you make a first jump, then again make a second jump. So basically you want to see at which location are you landing on. And if you have taken infinite number of jump, and you are around some, when you are in the neighborhood of some number, even after taking the infinite jump, you can say that this particular point at which you are in the neighborhood is basically my limit of sequence. It's the same exact thing. Instead of going continuously, now you're going in a discrete steps. So again, the whole definition all fits. Okay, can you explain the definition of okay.
So can I explain the mod an minus L
Yeah,
less than
sure. I'll so just a minute. So the idea is that when we talk about sequence, this en, right? So this basically represents, it starts from some n, and let's say it possibly might go to infinity. I don't know. So I'm basically considering an example of infinite sequence. Okay, So I'm basically trying to understand what happens to this. You can see this whole thing as this, right? For example, if I want to compare this with the limits what we studied before, they are almost same thing. They are exactly same thing. Now what happens in the case of limit, you are basically interested, you were interested in this x naught, right? Some x naught. So you had some x. Now you are trying to approach from x to x naught. The thing is that this approach can be also done in a steps, not in a continuous fashion, and that can be seen as, for example, x1, x2, x3, x4, such that my x infinity turns out to be some x naught. Okay, so that's what the idea of the sequence tells you here. So I'm approaching this x to some x naught, and the way, if you recollect the ideas what we used in the limits, that we had this some f of x function, and we just want to understand what happens, uh, basically this, when x tends to x naught, right? So this is what we want to understand. So in that example, if you remember that we mentioned this, right? For example, for all epsilon greater than 0, there exists delta greater than 0, such that for all delta x minus, sorry, x minus x naught is less than delta. Is this idea clear, that what we have did in the case of limits? Now instead of going into continuous fashion, we are now going in the terms of steps. Okay, so that's the difference. So what happens over here? So now I just want to define this part separately, right? So what I'm actually trying to do here, let's say this number line, right? This is my target x naught, because at this point I'm interested. So what I'll do, I'll make this target as my limit of sequence to which I'm interested, right? And I'll approach this via a jumps. For example, I start with this x1. I start from here, x1, some x1, which is a fairly distance from this x0, and I'll start making a jumps. I'll make one jump, and then I will calculate again. I make a one jump again. I'll calculate. So thing is that I'll keep on making jumps such that my infinite jump would be the x0. So I will try to define this. How can we write this mathematically? So the idea is that I can see this thing, a sequence, right? Some kind of a sequence. So what happens here? What I'm trying to see here, that whether this sequence xn converges to x naught when n tends to infinity. The way we can write this is that xn minus x naught, the distance between them is less than some interval, right? The same thing which we did earlier, right? The same thing which we had definitions about. So this basically tells you distance of some sequence, some nth sequence, for example, with limit, right? And I see that this distance is less than arbitrarily small for a given, for a given for a given interval, and this basically makes an interval around this. Okay, so if you interpret this, this turns out to be that we have this x naught plus l, x naught minus l, right? And what you see that, because I can always write this as this, right? Xn minus x naught, sorry, I actually made a mistake here. It's not l, epsilon. Basically I have created a neighborhood right over here around x naught. So what I see that after some steps, what I see that all the elements of the sequence start fall into this interval, right? and you can see from here itself. So you can see my sequence element start falls into this. You can see this subsequence. I mean this in neighborhood, not sorry subsequence. So you can see that. So you define the interval around this, the neighborhood around this limiting value. I can always come up now instead of delta. Now instead of delta, since in this case we had this continuous example, right, where I'm approaching x continuously to the x naught, but in this case I can see I'm not approaching x naught continuously. Instead I'm approaching step by step. So what do I see, that after a certain step, let's say n naught, which belongs to the natural number, there exists certain step after which all my elements of a sequence will start fall into this neighborhood around my limit. So this is how I define that my sequence is convergent, and that convergent is x naught. Is this idea clear to you? Hopefully, like
Sir,
yes.
sir, but x1, x2, x3, and the starting elements don't fall into the
No,
neighborhood. Then
no,
how
no,
can I
no.
stabilize them?
It start fall into the neighbor after some step, after some critical step, right? So that critical n actually depends on epsilon. This n naught actually depends on the epsilon, the interval which you create. Let's say I made an interval like this, for example, this kind of an interval. For example, x naught plus epsilon, x naught minus epsilon. In this case, you can see all my terms fall into this neighborhood, right? But the problem with this neighborhood is that I don't have much confidence on my answer, right? The more shorter interval would be, the more confident I would be, right, about this limiting value. This is idea clear to you?
Yes, sir.
So that's what this that was this modulus tells you. Where that's what the definition tells you. That's how we define the way we approach to a point. So the thing which I have defined here, for example, like this is nothing but only this part of the original limit definition. Only this part. In the original definition of limits, you might have seen where we are trying to approach to a particular 8 port, that is x naught, right? But
Yes,
this approach is continuous. But over here, what I did, I made an discrete steps. In the terms of discrete steps, I'm making an approach to a particular limiting value to which I'm interested to calculate the function, right? So that's the idea. So we can see this. So basically, in the x-axis, you can approach in this way. So you can create this discrete step through some function. Like for example, I can give you one example. Let's say I want to approach. mm, uh, let's say in this case example, let me take this example. Let's say I want to approach number 0 here, but I can approach by this way, right? -2, then some positive number. You can see this way, right? I can approach oscillatory, right, by selecting these discrete values. But you can see as my number increases, as my n increases, my value start getting more closer and closer to 0, right? Is it clear to you what is happening here? Like,
yes, sir.
so the main idea is that you have to see the distance between the elements. Distance. If the distance is getting closer and closer, we can expect some convergence. If the discrete is not getting closer and closer, then it's very hard to see any convergence. For example, in the oscillatory thing, right? The +1 -1 +1 -1. Even though all these sequence elements are plus and minus 1, but you can see there is no convergence because I can always have +1 or -1 in the given interval, right? Because for example, if I have this +1 -1, right? This kind of jumps, I can always have either plus or -1 at any given interval, right?
Yes, sir.
So that's the problem. So this actually violates my idea, because I can always have some convergent value to be +1, some -1. So there is no unique, I mean to say. So in the given neighborhood, all the points do not map to the same number. That's why we don't see this over here to be some kind of a convergence. So that's an example here. And the thing which I want to say next, I hope this definition is clear and all. Uh, so only difference between the sequences and the things which we have studied earlier is that instead of going continuously, now going in the steps. So you will see that instead of writing functions over here, now you are writing this way. Just same thing, right? You can see this is that's another way of writing this f of x. You can say, right? This, I mean, I will not say f of x. I would be wrong here, but I would like to say this f of n. You can say left hand side. There is the left hand side actually represents the element of a sequence, and right hand side shows you that how my sequence is being generated, right? And we just want to know whether this sequence is convergent or not. And convergent in the sense that when you take n tends to infinity. So in this case, in this example, we are always interested in this n tends to infinity. Always. I mean, there is nothing called as n tends to 1, n tends to 3. We are always interested only in this n tends to infinity. Why? Because this an turns out to be some input of function, right? Because in this example, as I've showed you here, right, I've just defined this. I have just defined this part. I have just defined this in this whole thing, right? And here you can see this actually turns out to be some input, right? There again I'll start doing something, because instead of writing f of x, for example, 5, instead of writing f of 5, I would consider myself to write as this, such that my an tends to 5 when n tends to infinity, right? So the idea is that your function might not be defined at x equal to 5, right? You might not be, you don't have this definition. For example, you don't have definition of f of 5. Let's say the function is not defined at 5. So how will you do analysis, right? So the one way we can do the analysis, instead of taking an input 5, we will take an input a of n, a sub n. We'll take an input as a sequence, right? So instead of putting 5, yeah, what we'll do, we will make an input as a sequence, and we will slowly and gradually move. I mean, we'll slowly gradually approach to 5, like this way. So this is what we call as a sequence approach. You can say sequential approach. So that's the idea here. I hope this idea is clear to you, right? So why the sequence and series are so important? Because this gives you another tool, another approach to do the analysis at a point for which the function is not defined. Okay, so that is the idea here. And we are always interested in the idea that whether this function is convergent, divergent, oscillatory, and what. Because if my sequence is not convergent, then that sequence is not much useful to me. Because the idea is that, because in the back of my head I have this concept, right? On back of my head I always have this concept. Because if this is not convergent, I mean, then I don't know where I'm doing my analysis, right? So we are always interested in to know whether this function is convergent, divergent, and oscillatory. Because oscillatory is also an example, because for example, if we have sine function, I mean, if you want to basically do something called as oscillatory analysis. In the case of oscillatory analysis, we use this oscillatory sequence, because we do this because, you know, sometimes we are interested to calculate something called as frequencies of oscillations. Basically it tells you something called as time period, right? Let's say you have some problem. Let's say you have some problem in front of you. There is some system which has some periodic behavior, or let's say which has something called as oscillatory periodic behavior, right? And you are interested in to do calculate what is time period and all. So this oscillatory analysis will help you to basically do that calculation. And in that case, we use this oscillatory sequences a lot. So it depends on what kind of analysis you want to do. Based on that, you use the sequences. So where you can use the divergence sequence. So the place where we can use the divergence sequence for values of x such that where my f of x tends to infinity. Basically, wherever I do have this, vertical asymptotes. For example, like this, let's say I have this vertical asymptote and function behaves this way, right? Here you can see there's a vertical asymptote, right? And let's say I want to do the analysis of function. Let's say this is my function f of x, and let's say this is some x naught, right? Okay, so I want to do the analysis of this, right? For example, where do I see this asymptotes? So I would like to study this analysis via a sequence. You can see here, right? So what do I see here? This turns out to be some infinite when h n tends to some x naught after, you can see here. So the way we can approach this n tends to x naught is via a sequence. So I'm just keep motivating you. So why do we study this idea of convergence, divergence, oscillatory? It depends on the various mathematical situation. You use that corresponding sequence to work with. Okay, and I will share this PDF. This PDF you can find them in Google Drive. You can read them. This PDF is very simple. Everything is written in a very crystal clear manner. So just by reading you will understand like what's the idea and everything. And there is something called as infinite series. Then we talk about something called as, so first let me make you understand what do we mean by a series. So series is nothing but basically summation. You can sum of sequences. You can say sum of sequence. Uh, Sum of sequence element, I would say. Sequence elements. In the very layman language, I'm saying. As you can see from here, you're summing up all the elements. So the quantity which you end up is something called as a series. And when we say that it's of infinite series, when the number of I mean if the elements in the series is infinite, right? Let's say why is this summation infinity? Because my sequence is an infinite sequence. That's why my in series I see that there is infinity in the summation, right? So if my sequence were finite, then I would see a finite series, not the infinite series. So infinite finite is because of that we have something called as infinite number of terms in a sequence, or maybe finite number of terms in a sequence. Then we define something called as a partial sum, because partial sum is also an amazing. So partial sum is an idea in which you can basically go from a series, some idea, something called as a series object, something called as a sequence object. Let's say you are not good in handling call as series. Let's say you're very bad in to work with series. So what you can do, using this partial sum, you can convert your series problem into a sequence problem, right? As you can see from here, the way we define the sequence, partial sequence, is this, right? And this partial sequence will become a new element of a new series. For example, let me write down over here. So what I'm basically trying to say here, for example, if I had this series a1, a2, a3, and let's say an. So what I'll do, I'll define a new series, a new sequence. This is my sequence. I'll define a new sequence, and these two sequences are related. They are very related sequence. I will basically use the elements of the old series, so old sequence, to create a new sequence using this. I'll do this like S1 would be just A1, S2 would be the A1 plus E2, S3 equal to the A1 plus E2 plus A3. And you can see again I have a series, right? A new series. And this series and this series are related. Okay, so So here I can see that I have converted the idea of series into a sequence. And so if someone asks me that I have a series, for example this, so what is the value of s? So what is the value of s? So instead of talking in this language, we can alternatively you can talk in this language, right? They are again related. And how they are related, as you can see from above side. So this is the idea of partial sequences, partial sum. Basically each partial sum is an element of a sequence, right? And you want to know what is the limiting value of that partial sum series, I mean sequence, sorry, sequence. So this limiting value will basically tell me what is this. So instead of talking in the terms of sequences, now we are talking in the terms of series. We can see now the whole discussion turns into basically what is my limiting value of a sequence. Now you can do various tests to know what are the limiting values. For example, you have this one ratio test, right? You have this root test, then we have something called as integral test. You can find them. And then we also have something called as Leibniz Leibniz, okay, test. This test basically tells you whether this particular sequence is conditionally convergent or it's an absolute convergence. And that is very important because all absolute convergence are convergent, but conditionally convergent means they are convergent but with a pinch of salt. You have to take that with a pinch of salt. The idea behind this pinch of salt is the word is conditional. It depends on what condition, how you're treating them basically. Conditional in the sense like, convergence, point of convergence, I mean to say the point of convergence depends on the way you treat the series, let's say sequence. I'm using series and sequence synonym because you can always convert them to each other. So that's the idea behind this conditional convergence. If you rearrange your terms such that you have a convergence, but the point of convergence will be different. Because the idea one which you saw earlier, this 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5, right? And this actually turns out to be some log of logarithmic base e2, right? So this is an example which is taught in the classroom. And you can see when you do this kind of an arrangement of the terms, it turns out to be that the summation is ln2. But what if I do this kind of an arrangement where I collect all the even terms in single bracket, and what if I collect all the odd terms, I mean odd even in a single, then what do we see that this is not equal to log e2. So the point of convergence depends on the rearrangement of the terms you do. Okay, you can check them. And this uh, conditional convergence are the favorite series sequences. You can say, all these crazy things. The thing is that why is it not log 2? Because you can do the analysis. You can find various other videos in the YouTube based on this conditional convergence. The idea is that in the case of conditional convergence, it depends on how the way you treat this series and sequences. Basically, how you treat them. Basically, it depends on the arrangement. The moment you change the methodology of doing the convergence, I mean to find the convergent value, your answer will get changed. This is a very strange because uh, you see these results, right? uh, you see this very bizarre result, like summation of all integers turns out to be some 1 over minus 12, right? You see some this kind of bizarre results. So you can create this result. You can find YouTube videos. There are so many other YouTube videos. I will post one of them in the description of this in this video. Over there, we will see that they use this conditional convergence to prove this result. They use this they start with some oscillatory functions, right? They start with this oscillatory I don't remember the proofs, that's why I'm not displaying here. That's not my goal. So they start with some sequence, let's say plus 1 minus 1. They start with this oscillatory terms, and you can see that the way you can arrange, it depends on arrangement, right? If I do this kind of an arrangement, let's say this arrangement, then you can see this series turns out to be 0. But the moment I change some different arrangement, let's say if I collect all my plus ones to the left hand side, all the minus to the left hand side, this might be greater than 0, might be less than 0. So conditional convergence is not easy because you don't have a fixed unique, convergence point. If your series had a unique convergence fixed point, a unique point of convergence, then why would it be a conditional? The reason conditional is that it depends on the condition. It depends on your analysis. In the case of absolute convergence, no matter what you do, the point of convergence is unique, right? So this is the clear difference you need to understand. And usually we see this kind of conditional convergence whenever we have this oscillatory plus minus behavior. This is very common. They are very common examples. For example, if you see this, you might have seen this example, right? S equal to summation 1 over n square and tends to 1 to infinity, right? This turns out to be some pi square over 6. Strange. You can find the proof of this, like geometrical proof. There is one video by 1 blue red 3 brown, this YouTube channel. You can check in this video. He will show this. Why is this sum equal to pi square over 16 geometrically, pi square over 6 geometrically, without doing any algebra? Because this pi square over 6, it is very deep rooted in the idea of geometry. It's very deep rooted. So the reason why I picked this example, because the moment you add an oscillatory term here, then this becomes an headache. In this case it is convergent. In this case it is convergent. In this case it is still convergent. I mean, you will still end up with some absolute convergence. But in this example, which was this is conditional. There is one result you need to remember. Maybe you can prove them. You will find this in every book. You can also find this over here as well. I can show you that. This is a very, very important result. Yeah, this one. A P series test. You can see that you have this infinite series. And this series turns out to be convergent only when you have P greater than 1. Otherwise, that's a divergent. But you can make this. You can make this conditionally convergent. You can make this conditional convergent when you add this oscillatory term to this. Like for example, this. So this becomes conditional convergent even for the P equal to 1. But for P equal to 1, you see that this is divergent. So this oscillatory does a very funny behavior. Very, very funny behavior. And the way we can test this is via this Leibniz test, right? This Leibniz test. Because the idea behind the Leibniz test is that, see, here you have the convergence because of the oscillatory cancellation. Now let's ignore this oscillatory cancellation. Let's say if all the terms were absolutely positive, because in the Leibniz test you basically try to calculate this, right? If you see this is actually greater than equal to this, and you can see this is because of the triangles inequality of them. This is because this is the property of modulus function, right? Because x plus y is always less than equal to the mod x plus mod y. This is what I'm using here. So if this turns out to be and convergent, then we say that this is definitely convergent, because this is strictly less than this. Because what do we see that this guy is strictly less than this. So if this is convergent, then for sure this is convergent, and that's why we have this unique convergence point of convergence. But what happens in the case of conditional convergence? This is not convergent. I can give you one example, and that example is this. Let's say you have this oscillatory behavior, uh, 1 over n, and n is 1 to infinity. We can see that this s is less than equal to, in this case it is strictly less than. See, this equality happens when all are positive, right? But we see that over here all the terms are not positive. Basically, not all the terms are in the same sign, they are of different sign. So what do we see here is this, and this is definitely not convergent. So if this is not convergent, this if this is not convergent, then you cannot guarantee the absolute convergence of this. Cannot guarantee. Okay, so that's the idea. I hope this all this idea is clear to all, right? Okay, so there's one question here. So, but when n tends to infinity, 1 over n tends to, yeah, definitely it becomes 0. There is no question in that. The problem is not that, the problem is not the idea that this goes to 0 as n tends to infinity. The problem is in the summation. Try to understand, we are trying to add. If you see the second lecture based on this infinite series given by professor, you will see that he proved that this sum, he proved this, like this s equal to infinite sum of this is divergent, right? And you can see the same proof over here as well. This, in this case, you can see they first proved this, and for over here they did this. So you can see another proof here. So the one which you said here is this. Here you can see they proved it, like this infinite sum is divergent. You can see from here. Okay, so you can check this PDF. You can also check the ideas. But what I'm saying you that I'm basically trying to explain you this Leibniz rule. I mean this Leibniz test to basically verify whether your given series is absolute convergence or conditional convergence. So when you have this conditional convergence, you need to be very careful, extremely careful when you are dealing with this conditional convergence series, because the arrangement of terms will change your answer. And using this conditional convergence, you somehow able to create this funny results. To me this is very funny result, and this is the manifestation of this conditional convergence. Okay, so you need to be very careful, I mean to say, especially whenever you have infinities are whenever infinities are involved in your problem. You need to be extremely careful whenever infinities are involved. And here you can see definitely infinities are involved, because here we have infinite terms, even though this each term in a very long run, you see it tends to 0, but it doesn't seems to add in a same sense, because the way the cancellation happens in this arrangement, the same cancellation doesn't happen in this combination. Let's say if you take a pair of 3, pair of 4, and you try to do cancellation and do addition, it turns out it doesn't work the same way. So it's a very headache. I mean to say, you need to be very careful with such. So I would recommend you to please go through this. Okay, the test for the convergence of an infinite series. I guess this result itself enough, right? Because you can convert all your problems into this, right? So the idea is that we have something called as Taylor series. You also have something called as Laurent series. I don't know. You guys have heard this Laurent series. I'm not sure if you guys have heard this Laurent series. There is something called as the Taylor series, and there is something called as the Laurent series. So I'm sure that you guys have heard this Laurent Taylor series. Laurent series turns out to be the more general series. Taylor series can be written down if you don't have something called as singularities. I mean, I don't know if you guys know what you mean by singularities. So singularity is basically where your function is not defined. For example, let's say f of x equal to 1 over x minus 1. So in this function, the singularity is actually x equal to 1. X equal to 1 is a singularity point, a singular point, right? Where basically function blows up. So, wherever your function, when you're basically, this is your function, right? So this is your function over here. And if you want to expand this function in the terms of polynomials, powers of, I mean, in terms of polynomials, in the terms of powers of x. So you can do that. You can always do that using the Taylor series, but the condition is when you're writing the series, you write about some point, right? For example, in the case of Maclaurin series, I don't know the spelling, I forgot the spelling. Maclaurin, I guess. Maclaurin series. Basically, you write down the series, uh, you know, in terms of x, and not in terms of, sorry, I used very wrong word, at point, in terms of series at x equal to 0. So if someone tells you, give me a series, give me a polynomial series of this function, give me the series which is in the terms of x powers. So the first question you need to ask, about which point. So in the case of Maclaurin series, we write the series at x equal to 0, and Taylor's is basically is a generalization. Basically, in the case of Taylor series, you write series at x equal to some arbitrary point, let's say x equal to a. So if you take x equal to 0, then your Taylor series becomes Maclaurin series. So Maclaurin series is a special case of Taylor series, and turns out that Taylor series is also a special case of something called as Laurent series. Laurent series is a bigger class of series. The problem with the Taylor series is that it cannot handle singularity. I mean, you cannot write down series about singularity. For example, if I ask you, everybody knows how to write down series for sin x, cos x, and all. But if I ask you this particular function, for example, this, and write down a series about x equal to 1, let's say at x equal to 1, your Taylor series will fail badly. Your Taylor series will fail badly, right? So Taylor series won't be able to handle this problem. So whenever you have singularities in your function and you want to figure out what is the series about that point, we use something called as a Laurent series. Okay, so Laurent series has basically two parts. One part is Taylor, the usual Taylor, and the second part is basically what is singular part. Basically, the singular part takes care of the unusual behavior, right? So whenever you don't have this singular, all your singular part will become 0. I mean, I just don't want to get into the details, but the idea is that you need to be very careful wherever you have singularities. For example, here, so whenever you're trying to write down a series about a point which turns out to be a singular point of a function, then please open your ears carefully. I mean, just see what you're trying to do. So make sure that point is not a singular point. So if that is a singular point, then you have to use Laurent series. That takes care of the singularities and everything. I hope you guys came to know something new, right? Okay, so sounds good. So why do I started all this discussion? Because okay, so the reason I started all this discussion, because just by knowing this thing, just by knowing this just by knowing this, you can basically solve any problem, because you can always write down a series in the terms of powers, right? And then you can check whether each of these particular term is convergent or not. If you guys are little confused, then let me write down the Lorentz series for you. So basically, Lorentz series actually looks like this, and this goes from minus infinity to, let's say, plus infinity. Here you can see, right? It has both. So this is Lorentz series. And if you want to see your good old Taylor series, let me expand this, and you can see the Taylor series is embedded in this. And you can write this, right? Let me write this 1 infinity, and here you can see that. Let me write this as this, right? I hope this is clear to all, like what I have done here. So if a series is convergent by one convergence test but fails in other convergence, does it imply the series is at all convergent or conditional? No. If you are trying to test whether this is absolutely convergent or conditionally convergent, then doing that test you can only say whether that's absolutely or conditionally. But when you are trying to test using absolute convergence tools, root test, okay, let me tell you the level of convergence. So first we have level 1 test, and that level 1 basically, in which you basically test whether that is conditional versus absolute. Okay, so if it's conditional convergence, then you stop there, you don't do anything. And the moment you find that's an absolute convergence, then you have this level 2, you have this root test, right? So when you're applying the root test and all, at the back of your head, you know that if this test is a successful test, root test, ratio test, if all these tests are successful tests, then definitely my series is absolutely converged, because this root test, absolute test, and those various tests, this level 2 convergence, this level 2 test, all this depends on the fact that your original series was absolute convergence. I would say don't connect them. I would say they are different. They are independent statements. I'm saying because of my own experience that you should see them as a different thing. Conditional versus absolute test is a very different thing. Don't mix that with the ratio test and absolute test. I can give you one example. For example, in the case of conditional and absolute, you basically check, is this convergent, right? We have this basic question of this, right? Is this goes to 0, right? We have
You
this
mean
question.
mod of A in as a sequence or as a series?
I would say as a sequence, yeah, as a sequence, you can
Okay.
see. So you have this question. So in order to test this mod of an, you use this root test, ratio test, and other things. Okay, but okay, so I think so this is not possible to us. Yeah. Hmm.
Okay. My one question, that
Yeah,
is,
yeah.
how do I know which convergence test is for absolute convergence test or which
Leibniz,
one for conditional?
it's just a Leibniz. This is what
Okay.
I'm doing, right? Basically, I calculate this. See, the conditional and absolute is for a series, not for a sequence, right? You can always convert a series into a sequence, which I've told earlier. But the idea is that you are checking this, right? This kind of fashion, right? You're checking this. So we see that the difference between the conditional and the absolute is that we have something called as oscillatory behavior, which do some cancellation and make it convergence. But in the case of absolute, we avoid those possibilities by taking this modulus, right? I hope this is clear to what I'm trying to say here. Uh, uh, so whenever you want to test whether this is conditional or absolute, you go with this test. You check whether this is convergent or not. If this is convergent, this particular thing is convergent, then we say that that's absolute convergent. That's absolutely convergent.
Also, we can use Westra's M test to prove a series convergent or not, right?
So in the yeah, that is also a tool. That is also a tool. But I don't think so. That that kind of angle would be asked in questions. Mostly they would be focused on root test, ratio test, maybe Leibniz test. That's it. Okay.
Okay.
The test which you told is comes under real analysis course, which is the next level course of this. That is more advanced tool. So yeah, you are definitely true. That's true. So what I was basically trying to say that no, this ratio test, root test is basically tells you the convergence of a sequence. Let's say you are in a picture of a sequence and you want to test the convergence. At that time, you use this root test, ratio test. But now in this left hand case, you are in the picture of series and you want to test whether this series is conditional or absolute. At that time, you use this Leibniz test and everything. I hope all this idea is clear. So, can a convergent series be proved convergent by all sort of convergence? See, whenever we say it's a convergent series, you also need to add another word, that is absolute or condition. So you just don't write that's a convergent series.
Uh, I mean absolute.
Yeah, absolute. Yeah, then it's true.
So for an absolute convergence series, can we prove that it is convergent
Yeah.
by all sort of absolute convergence tests?
Yes, yes.
Okay.
If it's absolute convergence, no matter what technique you use, it will always give you the same answer. And the reason behind is that because it has a unique convergence. That's why it works always. And we are always interested in the absolute convergence because as far as we are working in industry, as far as we are doing engineering, we know that in physics, in natural sciences, we have a unique convergence because that's what we see. So I was in the Lorentz series. So what I was trying to say here that you can see this is the Lorentz series. You can see you have this negative powers, positive powers. So when you just open up, like for example, this and this, right? I have made this 1 to infinity by redefining my n. Okay, so don't get confused. And you can see here my an is nothing but just this, your right. And we will not talk about this bn for now. This bn has something to do with something else. So thing is that this Lorentz series has two parts. One your good old Taylor, right? And you have this singular part. Okay, so so Lorentz series is always true, no matter what kind of point that x naught is. So if your x naught is a singular point, then you see that this singular part becomes essential, right? Because that is the important part now. But when x naught is not a singular point, then we can say Taylor part is more important. So depending on the situation of x naught, because this series takes care of all possibilities. So Lorentz series is a very good series, and you can say Taylor series is a special case of, I can say a part of a Lorentz series. We will study all of this in a subject called as complex analysis, because in the complex analysis we are interested at a point. For example, see, in complex analysis we basically have a fabric, right? In a fabric there is a puncture, and we are interested the behavior at that puncture point. Okay, so I hope what I'm trying to say. So you can see all these things are how related. So whatever things which are currently reading, that turns out to be one of the prerequisites of complex analysis, which is more general, more important, where you will be using almost everywhere, right? We can see the same picture again goes carry forward. Okay. Can you see background music, background sound? If you are unable to hear me, then you can postpone this because today is festival, I think. So let me move forward. And okay, you can see all those things, repetitive things, and you can see there is a various tests, right? So in this section, you can also see comparison of various tests. For example, you have two series, and you want to just check the convergence. So let's say, because we can always make some relation between the sequences, right? And based on this relation, we can comment on the convergence of one of the series. For example, you have uh, this a series and you don't know about the convergence, but you know the convergence of this, but you don't know about the first part. So based on doing the simple comparison of the elements of the terms, you can comment what would be the convergence of my original one. So here is one of the example in which you can see that where they have considered summation Vn to be convergent, and they want to check whether the summation Un is convergent or not. So they have listed out schemes in which the first point tells you that Vn should be strictly greater than Un. So here you can see that this is somewhat like a sandwich theorem. Okay, half of the sandwich theorem. Uh, so if my bigger function is convergent, then my all the functions which is bounded by that bigger function is always convergent, right? So the idea behind that is, let's say this is my convergence, okay, and I have this function like this converges like this. So this is n, and this is some, depends on what it is. So let's say this is some Vn, and you have this u1. Sorry. Now you can see if my Vn is get converged, right, to some convergence, then also you can see that un also getting converged. Maybe not exactly that point, maybe somewhere else, but I think so they have made a mistake here. Oh no, they have taken care, they have wrote this positive term, and that's the key important term, because if that's not true, then you might go to the negative infinity, right? And that is not convergent thing. And since they have given this, so this also eliminates the possibility of oscillations. But since this is one of the part, there is another part, that is the ratio, and the ratio turns out to be finite, and it has to be greater than 0, and if we take the limit of this ratio, that turns out to be some finite value. So this, all this B and C point basically ensures that you don't have this behavior. This eventually ends up somewhere here to some convergence. Most probably it will converge to the same convergence because of this equality in this comparison. So I have left this diagram here so that you can make a geometrical interpretation out of it. And the second point also, they have given that if we have two sequences here, and this is very important, you shouldn't forget this point, right? They are positive terms, and we have again let this to become divergent. Then how can we say that my given function is also divergent? Again same thing repeats, again same condition repeats. So I guess this would be much helpful in your questions. This is actually very trivial, even teacher has also discussed this class. If you are interested in the proof is also given underneath, where they have used the idea of partial sum, partial, and they have checked whether this partial sum is convergent or not. I'm trying to see some important points. I hope everybody know about this AP-GP formula, okay, and especially the infinite GP formula. This would be much more helpful. And I would also emphasize whether you guys know this, that AM, that arithmetic mean is greater than geometric mean, right? This basically tells you that if you have a sequence an, and if you just calculate what is the arithmetic mean, which turns out to be summation of an, let's say 1 to, let's say that's an infinite series. I'm not, let's make it a finite, then we will see what happens in the infinite level. And if you just calculate this, that's an arithmetic mean, right? And if you calculate what is the geometric mean, it turns out to be capital nth root pi of an. I hope everybody understand what is this pi notation tells you. It basically tells you the product. Okay, so this capital sigma tells you the summation, and the capital pi tells you take a product. So you see that am is greater than equal to gm, and this equality happens only when all your sequence, when all the elements of a sequence are equal. I mean to say that at least the ratios are same. So I will not consider this equality, but I'll assuming that all of my sequence elements are distinct. So see that we see this property, and maybe this would be helpful to solve one of your problems in exam. I'm giving a hint, right? Maybe this would be helpful, right? Because this is what your series is, and I guess you are interested in this. And maybe many of our problem calculating this is very simple, right? That is interesting. So this might be helpful. And if you are interested in the case of infinite limit, infinite series, then you just take limit n tends to infinity on both sides. So this analysis will give you for the infinite series. It's nice that I have discussed this, because this might be helpful in some of your problems if you get stumped. And how can you identify that I have to use this? You have to see whether the multiplication helps you or not. For example, you might have this, right? N factorial upon n plus 1 factorial, and you can see that this will help me. This particular tool which I've discussed now, this will help me to calculate the infinite series. I mean the infinite summation of this particular sequence, right? Because if I take a multiplication of the successive term, turns out to they cancel out, right? And you at the end you left with just 1 over n plus 1 factorial, and if you take a limit, this will turn out to be 0. So that's interesting. And over here we see that when n tends to infinity, this turns out to be 1. So this is not an interesting problem, right? This is not a convergent at all. So you will be able to check out whether this sequence is convergent or not. I mean, no, series is convergent or not, which is made up of this summation of sequences. This is important tool which I want to discuss. I guess you guys are familiar with EPGP. I just want to know like what exactly you guys want to know, because sequence and series is a very big topic. If you go into the computer science department, they have this semester course of this, just only sequence and series. You can understand it's such a big topic to cover. And let me see the important part. I'll go from down, because I guess you guys are pretty good with the simple equations. So these are some exercise. So these are some additional problems, I guess. The Cauchy root test is basically, so this is nothing more, just another name for the just a simple root test. So I guess everyone is familiar with this root test. So this basically tells you how can you comment about the convergence of a series just by doing this simple test written here, which is just nothing more than root test, where you do this and you check and you see that this turns out to be some limit.
Sir, may I ask what
Yeah,
book
yeah.
is this?
Yes, yes, yes.
So what book is
So
this?
this is not a book. This is actually a PDF of Ohio State University.
Sir, is it available for free online
Yeah,
reading?
yeah, yeah, it is available. But I will upload this PDF on Google Drive. You can download so that you don't
All
have to
right.
find. Okay? So the thing is that you know all these root tests, ratio tests, they are not just tests to check whether they are convergent or not. They give you very important information, and that is something called as the radius of convergence. They gave you something called as the radius of convergence. I don't know whether this thing is taught to you. Radius of convergence, and this radius of convergence idea basically tells you that the extent to which this is convergent. I can explain you this. Okay, let me do this. This sounds to be important. Let's say you have this sequence, right? This xn, and if you see the limiting value of this xn turns out to be some x naught, right? So basically, if you have this plane over here, you have this x naught. So this radius of convergence basically tells you a boundary around x naught, basically a neighborhood around the x naught, for which if you consider any point in this boundary, they all give you convergence, all. So yes, yes,
Sir, one question.
yeah.
Why is it called radius of convergence? Because we see radius as
Yes, yes.
a circle has a radius.
See radius. See, see, see what we are doing that. For example, if I have this neighborhood, right, I can make an approximate circle around it, right? So that's the idea here, making an approximate circle. But my actual is this, right? So that's an approximation, like approximate circle around it. That's why we say it's radius. The radius comes out because the type of function which you are dealing with is very symmetric. So that's why you see a radius. But in general, it might not be radius. The moment you go into the complex analysis and higher order dimensions, you don't see that very beautiful symmetries everywhere, especially when you are dealing with real life problems. So what do? We just have this approximate circle just to give an idea that the extent of convergence. So I'm saying this because this ratio test, for example, I'll start with the ratio test, which turns out to be limit n tends to infinity an plus 1 over an, which gives us a L, right? And based on that L, you say that's convergent or not, right? If L is greater than 1, it's not convergent, divergent. L equal to 1, you cannot say anything. L less than 1, that is convergent, right? And thing is that the radius R turns out to be the inverse of 1 over A. That's interesting, right? Because every time you are calculating this radius without knowing that you have been calculating radius. So what you can do that, you can make a circle around this x naught, and this radius tells you, it just gives you the convergence region. I mean, whatever the sequence you have defined. So yeah, that's a convergence here. I guess the more clarity of this convergence, area of convergence, radius of convergence, I guess this will get clear in the higher courses. But the idea is that if there is something called as radius of convergence, and let's say, for example, in the question they write that the radius of convergence turns out to be some 1.5, for example. So is the sequence convergent or not? Then you know what to do. Just make a reciprocal of it. This is inverse of 1.5, and that turns out to be less than 1 because this is nothing but the ratio test. And you can see that yeah, this series is convergent. That's the idea.
Sir,
Yeah.
sir, so this radius is similar to epsilon in the
No,
definition
no,
of
no,
limit.
no. That's a different thing. See, epsilon delta is basically They are also radius, but they are very small radius. Whenever you see epsilon and delta, right, this small Greek letters in mathematics, we see them to be positive number which is very close to zero, very close. They are used to define something called as neighborhoods. Okay, these quantities are defined to something. We use these variables to define the idea of neighborhood, right? But here you can see I'm using Greek letters R and L, so they might be big numbers as well. In mathematics, whenever we want to define something large values, we use this capital M, some capital letters. Is this idea clear to you? So this rate,
Yes.
so the clarity of this radius of convergence, this will get clear. I can give you one example of this radius of convergence and all. For example, you have this Taylor series, right? Let's say at a point. Now you can see that this is sorry, this is the Taylor series, right? At I've wrote this at x equal to a point, about x equal to a point. Okay. Do you understand what do I mean to say writing a series about a point? Do you understand what I'm trying to say here? Is this idea clear what I'm trying to say here? Writing a series about a point, that is important, because if you're not important, let me repeat this. Whenever I say writing a series about a point, that means I'm writing a series which is in the powers of x at x equal to a. You might be interested in doing the analysis at x equal to a. So what we write down, we basically write down this series in which you can see it is made up of derivatives, uh, single order derivative, higher order derivatives. So using these derivatives and this combination, we are able to write down the behavior of the function around x equal to a. Is this idea clear?
So we are taking the derivative in respect of a.
No, we are taking with respect to x and we are substituting a. So in case if you have a
Okay.
doubt here, let me write down what is that. We are taking the nth order derivative with respect to the x, then we substitute x equal to a.
Okay.
Is this clear? I guess this is what does it mean. Yeah. So over here you can see this is happening, right? I'm writing a function, a behavior of a function at x equal to a point. Basically tells you the
Okay.
neighboring behavior.
One more thing.
Yeah.
One more question. That is, when we are writing a point as a series, then does it mean the series is convergent at that point?
Yes, it depends on the yes. See, that depends on f of a. That depends on f of x. And this, the question which you asked, actually I'm trying to get to that point. That question exactly. I mean, I was trying to go to that question. Now you yourself asked me that question. So my actual question was that only. Whether this series is convergent or not, it depends on function. How? Let me tell you. Because now you can see that this is nothing more than this, right? Let me write this Cn so that there's confusion. There's no confusion. Is this clear to one? What I have written here? Cn is this. Now do your root test to check the convergence. How do you do the root test? You do this, right? L is nothing more. This limit n tend to infinity Cn plus 1 upon Cn, right? And that turns out to be some nth plus 1 derivative at a divided by nth derivative of a, and I guess then you have this n times, right? That's it. And the inverse of this is the radius of convergence. So you can see it depends on the function, right? The convergence depends on the function. If see this is convergent, so one thing I would like to tell you that if my x equal to a turns out to be analytical point, do you understand the analytical point? Analytical means just not singular. It is clear, like opposite of singular. So if my x equal to a is not a singular point, then definitely this will be conversion for sure. I'm just giving you a direct answer. I mean, there is a proof of everything. You will study them, but the idea is that this is an example in which you can see the importance of root test, ratio test, and all. And interestingly, your ratio test, if you calculate the ratio test, so root test turns out to be, if you calculate the value using root test and the ratio test, they also turns out to be same. More or less same. The same when convergent, I mean to say. When your sequence is convergent, then you see that the root test and ratio test will give you the same answer. And interestingly, the inverse of them is the radius of convergence. So now you can understand what this radius is trying to give me. It is trying to give me the radius, which is basically a minus r, sorry, a plus r, a minus r, and at this neighborhood, this series is convergent. Otherwise not. If you get out of this window, then your series is not true. Then your series is not convergent. This is basically blowing up. Now you guys can appreciate the importance of the radius of convergence, this ratio test, this all these ideas, right? Because, and now you can also see the reason why when you have this L greater than 1, you say that's divergent, because the inverse of L is basically a radius of convergence, and that turns out to be less than 1. And this doesn't make any sense. That's it. I mean, you also come to know about this in future, but the idea is that there is deep rooted geometry behind this, deep rooted geometry, and we call that geometry as analytical geometry. Yes, analytic geometry. So I hope the idea of this is clear, because you might have question like this. By the way, we also call this as the power series. Those who don't know, if you can search this. Let's say in this case this is Taylor series, because the Cn turns out to be this. This is Cn, right? But let's say if you don't have this particular Cn, you have just this form. This particular form is known as power series. And power series are very powerful tool. I mean, you can say Taylor series again. It's a special case of power series, where the Cn is related like this derivative thing of
Yeah.
function. So whenever we want to prove convergence, divergence, analytic, singular, and all, we always bring up the ideas of this power series. So these are some tools which I
So,
would like to share with you.
sir, one question.
Yeah.
That is, when you said that root test and ratio test are almost same.
Yeah, same.
So if they are close enough, then they are giving me two different limit points, right?
Yeah, that's why I'm saying, that's why I have used this word equal here.
So as long as the limit points are in those inside those boundaries, they are convergent.
Thing is that, see, the word which I use very close, they're actually, I mean, I've said it right, because let me frame it properly. I mean, very close in the sense they are equal. Next time I will discuss this point, okay? Because I think so I need to prepare that point. The question which you asked, because that's a very good question. But for now, you can consider them to be same. Because if you calculate the ratio test and limit, they actually turns out to be same. But there are still slight variation. Actually, thing is that there is other terms as well. In this case, and we in the limits they become 0. That's the idea. That's what actually I was trying to say. Actually, they should be equal. I mean, they are equal. I said they are very close because of this, non thing. So maybe I should recorrect myself here. They are equal.
I didn't get that. Could you try again?
I hope you got the idea. You got the point, right? What?
Sorry, I'm not able to make a phone call.
I once read that something like if limit points are in some sort of inside the interval, then they are convergent, something like that. I don't remember the exact theorem, but I saw something like that.
Yeah, it is true. I mean, actually, thing is that the reason I said, I guess, because there was some actually thing is that when we don't take this limit, right, there are additional terms involved here, and the moment we take the limit, this additional terms become zero, and we see them to be equal. So I think so because of that I said this. But the but see, when we the definition of root test and the ratio test comes when you take limit, right, and the moment we take limit, they are equal. So I better recorrect myself. Yeah, they are equal. But the condition applied that the sequence is convergent, then only they are equal. Otherwise not. Uh, because we have this extra term which don't cancel out to be zero. They will each of them will give you some different answer. Uh, any other question? I'll try to get some point from here. I guess ratio test is clear here. Oh, you can see there are two cases which have been discussed here. This case and this case, and they have given proof basically why we are saying it's convergent, why we are saying that's divergent. Over here, I have told you this geometrical thing here. That is called as radius of convergence. That's geometrical picture. The radius of, again I'm repeating, the radius of convergence basically tells you the neighborhood around that point to which this particular series is a valid series. Valid in the sense that series is convergent. I mean, you can see, right, because over here I have brought a behavior of a function at x equal to a, and here you can see this x is the neighborhood around that a, right? So how far this x can go with respect to a, and you can see that because of this convergence boundary, x cannot go beyond this boundary which is defined by the convergence, right? The moment your x is beyond this window, we see that this series is not convergent. This gets blows up, and you can see the idea that here the coefficient is always fraction. I mean, that's a fractional power. I mean, that's what is also captured here, right? It's like a fractional thing, so you can check that. I mean, just let's go to the next point. See, this PDF has full of questions, and they have covered all type of questions. I don't think so after solving this you will be having any problem anywhere. So over here you can see in the cases in the name of test, they all are using this ratio test. You will see mostly people using ratio test only. So there is one more test I would like to tell you. I think professor has not covered that, but still I would insist to have a look on that. That is known as, yeah, Rabi test. This is very important, Rabi test. For those who know that this Rabi is just not a mathematician. He has done important contribution in physics, known as something called as Rabi oscillations. This is very important, very fundamental oscillations which a system can have. So he has done much more things. So the idea that this test basically tells you by calculating this limit, and you have to see whether this k falls under which part. So if k is greater than 1, we see that that's a convergent, otherwise that's a divergent. So you can see here it gives opposite thing, right? Because in the case of ratio and in the case of ratio and the root test, we saw that when L is less than 1, then gives us the convergence. But here we see it's greater than 1, and also over here, if you guys don't know, then this is equal to the radius of convergence. This is not the 1 over r. Okay, in this case it is just r, and here you can see the idea that, and why am I saying that? Because you can see that's inverse of the what we have seen earlier. The fact that if this was convergent, then you can see un plus 1 over un was a fraction, right? So to make it greater than 1, he basically took the inverse of this and he subtracted 1 so that he can get the fractional part. So in the large limit,
Sir,
yeah,
one question. That is,
right.
so when we are finding the limiting value,
Mhm.
so the limiting value becomes the radius of
Yes,
convergence.
in this case, yes.
Okay.
I can explain you why. I can literally explain you why is this equal to radius of convergence. I can give you this reason. See, uh, un over un plus 1 over un. This limit turns out to be 1 over r, right? The radius of convergence when n tends to infinity, right? And we also know that un plus 1 over un, when my un is convergent, I'm taking the case of convergence, okay? So this ratio turns out to be 1 minute, less than 1, okay? So this ratio turns out to be less than 1 or n tends to infinity, right? So to make a fraction, we take this minus sign over this side, right? It's less than 0, but it's not 0, very close to 0, I mean to say. Then we multiply this n on both sides such that it becomes infinity times 0 indeterminate form. And the moment you take a limit, this actually falls under this r. Maybe I'm rushing too much. I think so. I've rushed too much here. Let me.
So could you explain why does it fall under R?
Uh, the thing is that if you see this particular case, un over un plus 1, this will be greater than 1, right? In the case of convergence.
Yes.
And to make a fraction, what I'll do, minus, we take a minus by 1. So this is a fraction which goes to very close to 0 when n goes to infinity,
Yes.
right? So to make a finite value, which is the radius, is greater than 1, we multiply with by n, because this goes to some infinity. Now we have this 0 times infinity fraction, this indeterminate form, and this turns out
So
to be
that is
1 by
why
r.
we are. So since it is an indeterminate form, that is why we are using R.
See, I'm not giving you the exact proof. In exact proof, you have to go through each step. Here I'm giving you the feeling how it is going through r. Here I'm trying to give you
So
a feel.
can we say since it is indeterminate form, that is why we
No,
are
no, no,
using
no.
R? Yes. Okay.
That's not a complete argument.
Okay.
I mean, I have to go through each step. That's a little big proof. You can find this. You can find this on internet. This turns out to be a radius of convergence, and we are always interested in this radius of convergence because we always want to know how much violation we can do. I mean, how much far we can go with this
Yeah,
radius
yeah,
of form. So you can see it is very important point. And here I was just trying to give you a feel like what is happening here. You can see this part, this guy is trying to go to infinity, right? And this whole part is trying to go to 0. And they have constructed in such a way that they give you this radius of convergence. The motivation behind the Rabi test is to basically calculate the radius of convergence. And in the doing so, he came up with this result actually. So that's what if you see the classic text, you will find that. So you can see this particular thing. I think so. I have spent enough time on this so that you guys now remember. Now let's go to the next point. Maybe I can find some. So many questions. I think so. Yeah, D'Alembert's ratio test. Yeah. So basically, the term you should use, the ratio test, is nothing but given by D'Alembert's same ratio test. So over here, he has just given a proof why this test works, how this test works. So he has used this idea of delta epsilon, neighborhood notation, definition of limits. Together, he figured out that yeah, this works. So in this case, they have given this proof. So here and over here also. For first he proved for the convergence, then second he proved for the divergence in this case. Then some note he had given. Yeah, the ratio test fails. Okay, that's important. Actually, I almost forgot about this. This is important. When the ratio test and your root test fails, so it fails when the ratios and the root test is equal to L. Whenever your L is 1, I mean to say, right? In this case, you cannot conclude. You might have divergent, you might have convergent, and a classic example of this is this. In this case, it's very hard to say whether this is convergent or divergent, because if you apply a ratio test or a root test, this will give you 1, and that is undeterminate way. I mean, not undeterminate way, I mean to say you need to come up with another result. Okay, that's why this object has a different proof altogether. And you can see from here that see now the convergence depends on P altogether. I think so. This is nothing new in this. I mean, this part in the sequence series is just all about doing calculations, solving as many problems as you can. I selected this PDF because they have given solution to all questions. I mean, along with the hints, notes, and caution, so that and each of the problem teaches you something. So that's how they are designed. So again, you can see all ratio test, root test. There's one important tool which I want to mention, that is called a sandwich theorem. You can use the sandwich theorem in this case. Thing is that, let's say if you have a sequence un, vn, wn, and they are this. Okay, if un goes to some L where n tends to infinity, and wn goes to L where n tends to infinity, then for sure vn will also goes to L and tend to infinity. So the picture here you can have is this sandwich thing. Right, the sandwich which we discussed earlier. I think so I have to erase this part. The convergence, and you are approaching dot by dot, and you can see so much of crowding here, crowding of points. And let's say this is your wn, pn, and let's say this is some plot n versus some f of n, depending on what sequence you are considering. So this is something called as sandwich theorem, you can say. I guess this sandwich theorem is a very casual name. I think so there is more accurate name for this, but I remember this as a sandwich theorem. I think so this is also given in this PDF somewhere. This question is important. I would recommend you to solve this problem. Uh, Nothing much. Do you guys have any questions so far? Uh, oh, okay. Important thing I left to talk about. There is something called as Cauchy sequence. Cauchy sequence. Uh, yeah, I have a note on this. Okay, so anyways, I'll start by myself. So Cauchy sequence is basically a convergent sequence. Basically, all Cauchy sequences are convergent sequence. So to which sequence do we call that's a Cauchy sequence? For example, if we have a sequence this, right? And what we are doing here, we are basically comparing the consecutive distance between the points. For example, if we had this was my line. I have this points here. Okay, so you can see that the distance between the points are now getting closer and closer, right? So Cauchy sequence basically a sequence in which the distance between this sequence element, we check the consecutive sequence elements, turns out to be vanishing as my n increases. So the way we write this, actually some people use consecutive distance, some people use two-step distance, three-step distance. Here I will write down the general distance between them. So basically we have this some sequence element am. We have some sequence element am, and we are comparing that sequence element. We are basically calculating distance between two elements am and an, and that distance turns out to be the interval which you gave me. Basically the precision, or you can say the accuracy to which they are 0. For all mn greater than n naught, which belongs to the natural number. So for all epsilon greater than 0, such that this is true. I think so. I have made a mistake here. I could have written more precisely. For all epsilon greater than 0, there exists m comma n belong to the natural numbers such that this is happening. So here you can check. We are basically trying to see the distance between the elements of the sequence, and that sequence and the distance between them turns out to be vanishing. And how do we define that vanishing? By using the interval which you gave me. So you gave me that interval to which this distance will be very close, such that I can always create m and n such that after that numbers, after that particular mth and nth elements, the distance turns out to be vanishing. So if you guys not clear what I mean to say, that is that am turns out to be an plus epsilon, an minus epsilon. So if I have a line, and let's say this is am, no, sorry. We have this an plus epsilon, an minus epsilon, and this also is sequence, right? Some a1, a2, a3. Now what happens? All your ams start lying in this interval, in this window which you created around an, and the size of the window is in your hand, because you know this window size is 2 epsilon. The more shorter the window you have, the more accuracy this am will have. So the more shorter this window, the more higher values of m and n you have to choose. So here we basically see the distance between these two elements. So and the thing is that this is little misleading. Whenever we say it's a Cauchy sequence, this is little misleading because we call those sequence a Cauchy sequence which satisfy this Cauchy criteria. So you better see this as a criterion rather than a sequence, some special sequence. Cauchy sequence is not a special sequence. I mean,
So every convergence sequence is a Cauchy sequence, right?
exactly. Because Cauchy at that time he was trying to find out a class of series, class of sequences which are convergent, and he basically actually ended up with a criteria. So if any sequence which satisfies this criteria turns out to be their convergent sequence. He thought that some of the sequence he has covered, but not all. I mean, when he was doing this, uh, he didn't generalize this to all convergent. At that time, he thought only those sequences which satisfy this criteria are convergent. But later, people figure out that all convergent sequences satisfy this criteria. All. And I guess the proof is given in the tutorials and everywhere. So I'm not dealing with that. I'm basically trying to motivate the idea. So you better see
Yeah.
this as a criteria rather than sequence. So I hesitate whenever I say the sequence. It's actually a criterion. It's a Cauchy criterion. So whenever, and this Cauchy criteria turns out to be necessary and sufficient. Do you guys understand the difference between necessary and sufficient? I guess I have discussed this in one of
I think
my.
sufficient is the weaker condition than necessary.
Uh, See, thing is that there is no comparison between necessary and sufficient. They are two totally different. Uh, Thing is that sufficient means if you check this, this is enough. Necessary means you have to check this. I mean, you cannot escape checking this. And if you have both necessary and sufficient, that means this is definitely you have to check, and this checking itself is enough. So, if I want to tell you that in statements, whenever we write statements, we have two parts, right? We have this part and this part. Uh, for example, milk is very good, right? So we have two parts, right? Milk and good. Okay, there is something which connects them. So this is what statement is. So whenever we have a statement, for example, a theorem, for example, here you can see this is the criteria. So whenever we have something called as necessary and sufficient, that means this statement is vice versa true. It is true from left to right as well as right to left, right? But when there is something called as necessity and sufficient, you might not have this double implied statement, right? So whenever we have something called as necessary and sufficient, that means you have to prove both sides, not just from left to right, you also have to prove from right to left. For example, in this case, we said that uh, those sequences which satisfy the Cauchy criteria is a convergent sequence. So when you try to prove this, you not only have to prove that idea that using this criteria, this is convergent, but you also have to prove that all convergent sequences follow this criteria. Then your
Yeah.
whole statement is clear. So
Yes.
so double implied statement. So I think so now everyone knows this. It's okay. You can discuss this. We can discuss this sometime. Uh, Let me check whether I have something missed.
Sir,
Yeah,
one one thing I have to say that
yeah, sure.
I I have seen that you have taught infimum supremum also
Yeah,
in other classes. So I have one question that
sure, sure.
we may discuss in the later class also. That is, my question is, in case of continuous functions, can we say that when infimum is equal to supremum, that implies right hand limit is equal to left hand limit?
Let me write down a statement so that we can have proper discussion. First, can you begin your statement?
In case of continuous functions or
Okay.
a sequence of continuous functions, can we say that
So the sequence of continuous functions, you mean to say, right?
either continuous functions or sequence of continuous functions?
Okay, I understood.
Can we say that when infimum is equal to supremum,
Mhm.
then the left hand limit is equal to right hand limit?
See, whenever you say that infimum is equal to the supremum, that means all of your, see, when we write the sequence of continuous function, it basically means this, right? Is this clear to you? Like what I have wrote here?
Yeah.
Okay. So
Yes.
basically, you are giving an input in terms of a sequence, right, to this function.
Yeah.
And what you see that since you have told that supremum is equal to the infimum, that means if this implies you that in range, if it's a range of function, there is only one element, right? Because that's the only
Hmm.
case when you have infimum and supremum to be same, right?
Hmm.
So what you see that in this case, every time you will get an output as L for all xn. That means all of your points are mapping to the same output. Same. If I draw a Venn diagram for this, you have this, right?
So, so
All are
my
mapping
question
to
is,
one.
can we see infimum and supremum as a left hand limit and right hand limit,
No,
and
no.
choosing the least upper least from the supreme least from the right hand limit and greatest from the left hand limits?
Okay, I'll come to that. First, do you understand what I have said here? Like we have discussed 2 points here. Like this is happening. Have you got this point? Because thing is that
Yes.
see in your question there is 2 parts, right? First is this. First part is this, where you have this infimum equal to supremum, right? And second part you connected this with the left hand limit and the right hand limit. The thing is that I just want to understand why are you connecting these 2 parts.
Because uh, when I'm actually drawing the diagram
Hmm.
of a left hand limit and right hand limit,
Mm-hmm.
somehow it gives me the intuition of infimum and supremum, which is not inside the interval, rather outside the interval.
Okay, let's say this was my point of limit to which I want to figure out, and this is my left hand side approach, right? And this is my right hand side approach.
Hmm.
Okay, and let's say this is my left hand limit, right? This is very close, I mean to say, and the right hand is somewhere here. See, if you see the definition of infimum and supremum, that basically tells you the maximum value of a range, right? I mean, you have,
Maximum when it is inside the interval.
yeah, I mean, let's say
I
this
mean,
way.
for a closed
Yeah,
interval, we
yeah,
can say that.
yeah. Let's say this, right? This is input set, and you have something called as output set CD. I'm making a box here. Okay, so you can see this distance is B minus A, right? This is B minus. So I basically made a box. Is this clear to you? And what do I see here? That in this box, infimum is here somewhere, and supremum is here, right? This is supremum, no?
Okay.
And this is your infimum. And over here you have this left hand limit. Over here you have this right hand limit. If you make the supremum and infimum same, that means you have a constant function, because that's the only case where you can have this, right? Let's say this is why this is my A and B, right? So what happens? There is a function. The input is A and B, which goes to only just one set. That is some L, for example, L. Here I can see infimum is this whole complete thing, and supremum is also this whole complete thing. In this case, my supremum and infimum
Okay.
is same,
Yeah.
right?
Yeah. I got it.
So in general, you don't have supremum and infimum to be same.
So if it is not a continuous, I mean, if it is not a constant function, then it is it can hold. It cannot hold, right?
Yeah, because and also you use the word something called as continuous, and I discussed everything in the context of continuous. If there was some discontinuity, then picture can go wrong altogether. You
Okay.
understand, right?
Okay.
And I don't
Yes.
and I don't think so. They will ask many things related to discontinuous functions.
No, this question came to my mind when I was revising these
Mhm.
concepts.
I hope this diagram is clear. Like this makes all
Yeah,
sense.
yeah, yeah. Sure, sure. Thank you very much.
Okay. So anything else? Any question?
So not right now, but everything you told, I understood that.
So you guys have my email, right? To which you can mail me. In case you don't have, you can note down. You can send your doubts, or maybe if you have something to discuss next time, you can email me. I'll continue the discussion. Okay. Oh, not
All
yet.
right, sir. Thank you.
Because I have not covered the sequence very series and sequence very properly. I think so. There are certain things still left to be discussed.
All right.
So this is my email.
Also, sir, I study Malik Aurora, and I do have Bartlett Harvard. For besides calculus books,
Mhm.
uh, I use calculus books by calculus and analysis by some author. I don't remember the
I think
name,
so.
but I
Thomas
use
Calculus.
that. No, sir. It is calculus and it's an old book,
Okay.
calculus and analysis by some. I sorry. The writer's name is Courant.
Mm-hmm.
So it's an old book though. I use that because I understood that the calculus is deeply rooted with real analysis.
Yes, definitely true.
So
But I would also encourage you to also have a geometry picture along with it. If you don't have a geometry picture, that means you have not understood.
yeah, yeah.
So I would insist you to go through a geometry picture as well. So there's nothing much.
So could you suggest some geometry books where it would be helpful
No,
to
no. I would just
understand?
I would suggest you to draw as much as possible.
Okay, okay,
So think
okay.
here I've drawn. So the question you asked me, what I did, I just drew it, right? And you yourself
All right.
came to know the answer. So try to draw as much as you can. If you are unable to draw, then ask. I think so. That's the best way you can learn the geometrical aspect.
Yeah, sure. Thank you.
So each and every statement which you read and you find that statement is unique, I didn't have, I don't have the geometrical idea. So try to make a draw. Try to make a picture of. I think so. In mathematics, you can have pictures for everything except you are in higher dimension. And I guess this course is calculus in one dimension, so everything is in a 2D plane. So you can always make a picture.
Sure, sure.
Okay. See you. We'll see you next time.
Sure. Sure.
I'll close it now.